In this lecture we talk about Galois categories. Now these Galois category is very important if we are talking about fundamental group of schemes, because at the end of the day, for proving such theorems we have to show that a particular object we are talking about is a Galois category. So for example, finite et al. Schemes, they are Galois category. So in this lecture we try to give a definition of a Galois category and give a simple example to understand what it is. So let C be a category and say F is a covariant functor from C to the category of sets. So this category of sets is finite sets. Now this category C with this functor F, so this category C with functor F, it satisfies the following 6 conditions. So there are 6 conditions which this category C and functor F satisfy. Then we call this pair of C and F as a Galois category, and this F is called a fundamental functor. So Galois category is a pair. You have a category C and you have a functor F. So this functor will take this category to finite sets, and then this category and this functor satisfy certain properties. So notice that we have to go to finite sets, because when we are talking about fundamental groups, we will essentially deal with this fundamental functor, and once you land in finite sets you can do all kind of things like automorphisms and things like that, which are not possible in general categories. So this is a very good tool to prove results about related to automorphism of objects, something which is like difficult to get handle on. If you make it a Galois category somehow, then you can prove things about it. So let us go through the axioms. So this category C has final, as final object is also called a terminal object, and a fiber product of any 2 objects over a third object exists in this category. So second axiom is the category has an initial object. Finite sums, or finite sums also called coproducts, exist in the category, and for any object in the category, so says you take any object in the category, you can form its quotient. So we can form the quotient of that object by a finite group of automorphisms. So what does it mean? More concretely, you take an object of the category, and in this object you have a group of automorphisms, and you take G as a finite subgroup. Then you can talk about Y modulo G. So obviously we need this group of automorphisms because fundamental group concerns about these automorphisms of covers. So you have this category C, its objects, you're talking about the automorphisms of these objects, then you should be able to modulo it out by finite subgroups. So the third axiom is, so say you're given a morphism in this category, it can be factored as U prime, U double prime. This is an epimorphism and this is a monomorphism. So you have X, you have Y, and you have Z. So this is our mapping U. So you should be able to form first U double prime. You have a surjective map here, and then you have a injective. Because we are working in a category, we cannot talk about surjective and injective maps unless we are in sets. But the idea is that you have an epimorphism first and a monomorphism. So the idea is that you should be able to take a monomorphism from X to Y. So X gets mapped to some object which injects into Y. So you can basically decompose Y into 2 parts. One part is just coming completely from X, and the other part is not lying in X. So this is an isomorphism of X with the direct summand of Y. So Y you can decompose into 2 parts. One part lies in the image of X and other part does not lie in the image of X. So this will be clear in an example. So this is the easiest possible thing you can do with a morphism. Then the functor F. Now we are talking about our functor, this nice functor here. This maps final objects are also called terminal objects to final objects, and commutes with fiber products. So fiber products you can think of as intersection of objects, because intersection of objects is as such not defined in a category. So you should be able to take these terminal objects and fiber products into sets, and this functor f also commutes with finite sums. So finite sums are called coproducts, and it commutes with quotients and maps epimorphisms to epimorphisms. And the last axiom is, if U is a morphism in the category such that f of U is an isomorphism, then U is an isomorphism. So if you see an isomorphism in the category of sets, it has to be the case that our Galois category also has that isomorphism. So we have to check all 6 of these axioms to show that some category is a Galois category. So the simplest example is that of category of sets and the fundamental functor, which is just the ID, because this functor f, once you apply to the category, you have to land in sets. So we are just taking the category C as sets, and the functor is just ID map. So let us check the axioms. So G1, so sets have a final object. So final object of sets is just a singleton. So any singleton becomes a final object, and then you can map one singleton to the another singleton by the universal mapping property. So say you're given maps f and g, and so then you can define the fiber product. So this is A to C, and then this is B to C. Then you can find the fiber product of this. So this is just the diagonal. So A comma B and A and B, such that GA maps to this, not GA, f of A maps to G of B, because you have f here and G here. So f of A maps to G of B. So the second one, so we have been able to talk about final objects and fiber products. So the second one, we have to talk about initial object. So the initial object is just the empty set. Then you have to talk about finite sums. So the finite sums are just disjoint unions, and the quotient group are just the orbit defined by the group action. So you just modulo out the group action. And then we talk about G3. So the epimorphisms are surjections. Here we talk about epimorphisms and monomorphisms, and monomorphisms are injections. And we can write a function in sets as a composition, like any mapping in set. You can write it as a composition of an injection and a surjection. So you can factorize a morphism like this in sets. And in particular, we are saying any monomorphism from x to y is an isomorphism of x with a direct summand of y. So this you can easily check right here. So say you're given an injective map like this, you can write y as u of x, and this direct so you have this disjoint union, and then you take out from here u of x. So you can see y can be written as a direct summand of the part coming into it, and then yeah, so essentially that part which comes from x and that part which does not come from x. And these functors 4, 5 and 6, they just follow trivially, because our functor is an identity functor. So it will map terminal objects to terminal objects, just going from set to set. So this functor doesn't do anything, it's just the identity map. And 4, 5 and 6 are all about this functor, fundamental functor f, which is just the ID map, so does not do anything. So we have given an example of a Galois category with a fundamental functor, the ID map.